Hi, hello. Thank you for attending this webinar. I'm Ronald Siat and Roman Martin will be here as well.
Hi, good morning.
This webinar will show you the new capabilities of the new release of CivilFEM for ANSYS 17.1. So, as many as you know, CivilFEM it's a civil engineering software based on the finite element method, and this software has capabilities and tools to which will will be adding to the ANSYS software. So this unique and powerful tool will have a wide range of civil engineering capabilities for any project, such as power plants, bridges, tunnels. You will see that CivilFEM has many modules. The main tools or capabilities of CivilFEM, which will be added to ANSYS, are the material library, extensive material library, which will cover the most international codes, and including nonlinear material models, full concrete material library, structural steel, reinforced steel library, pre-stressed soil and rocks. We have utilities for concrete modeling, interface for solid 65. Then we have as well the definition of cross sections. We can define any type of cross section for reinforced concrete or structural steel. Mechanical structural analysis and code properties will be automatically created and updated. We have for steel as well a library of hot roll shapes, more than 4,000 shapes available for AISC, the RBED libraries. We can define user-defined hot roll shapes as well. Generic sections by plates, we can merge, edit them. For concrete, we can reinforce them, and we can define as well sections in 2D with the mesh 200 elements, and then capture them to use them for mesh or beams. We can define combinations, smart load combinations, easy, fast, and we'll cover all typical civil engineering combinations. The loads are automatically combined and multiplied by variable coefficients in order to achieve maximum or minimum results predefined by the user. Main applications are mobile loads, code combination logic, actions in different directions, wind, earthquakes, or we can combine with variable coefficients, favorable and unfavorable. Many of you already know these capabilities. We can as well perform code checking or code design of reinforcement or steel structures or pre-stressed structures as well. Once the structure is checked or once our analysis has performed a structural analysis, we can later, after plotting displacement, stresses, or binding or moments or forces and moments, we can perform or carry out code on a standard checking. So we will see which elements will be okay or not okay according to the code specifications. It will be a kind of safety factor or margin of safety. And then we can create envelopes as well for maximum or minimum values. As you know, CivilFEM check the structure with an initial amount of reinforcement, for example, for concrete structures, and we'll show you the safety factor of each element. We'll take into account all the different loads and combinations and gives the optimized reinforcement. That's for ultimate limit state, but for the serviceability limit state, we can perform cracking analysis as well. And we have a complete range of codes, ACI codes, the Eurocode, British, Australian, Chinese code, Brazilian, Indian, for both concrete and steel. for beam and shell elements. Other capabilities are we can perform as well seismic response spectrum. We can, depending on codes, or we can create a user-defined as well. Besides this, CivilFEM has specialized modules for bridges and civil non-linearities, pre-stressed concrete, and geotechnical module. And the most advanced module is the nuclear power plant multidiscipline. We will cover all of the ones explained. These are some of our models. So, what are the new the new capabilities of this CivilFEM for ANSYS release 17.1? We have a new CivilFEM product launcher. This launcher will show we will see that we can open just ANSYS standalone before. Once you launch CivilFEM, you have a CivilFEM and ANSYS in our graphical user interface. If you just want to launch ANSYS without CivilFEM, you can do it just by launching the ANSYS launcher, the ANSYS mechanical PDL launcher. With this, you can see in this figure, this screenshot, the new CivilFEM launcher. You can you will see that we'll have a new license server. So new license for you will need new licenses for this 17.1 version, and this new server will allow you reconnections easily and with better usage and better connection. Before, once you lose your connection to a server, sometimes it's a little bit difficult to reconnect. Now it's improved. We add as well before, as you know, ANSYS you can use ANSYS borrowable license, but now with CivilFEM you can as well borrow license. Here you can see the new here. If you open the mechanical APDL product launcher, you will open just ANSYS. So you will see that CivilFEM is not shown in the main menu. But if you open our new CivilFEM product launcher, you will see that we can open then our new license server. You will see there. And then we have the final CivilFEM. If we want to open the CivilFEM and the ANSYS launcher, you will see there. You can do this. Okay. You have new other videos in our YouTube channel for installation on other CivilFEM capabilities for the license server, the launcher, how to borrow licenses. So you will have a complete video library here in YouTube. Other new capabilities are some codes. The new codes are the ACI 318, the 2014 version, and another version of the 349 for nuclear structures, the 2006. For steel structures, we have implemented the ASSC ASD 14th edition, and for AESTO LRFD bridge design, the version of 2012. Well, as you know, to select them, you can go to the civil setup options and choose from the drop-down list for steel and concrete. You can choose the new codes. What are the difference of these new codes? Well, mainly the strength reduction factor will be the main changes from one version to another, and the procedure is always the same. After after performing the structural analysis with the code checking and take into account the material pivots and the code specifications, for each section we will consider the interaction diagram, and for each section we will calculate these points of the actions and the ultimate strength of each cross section, and at the end we will have a total criterion. The same for the ACI 349. We'll show you later an example how to perform a code checking analysis in CivilFEM. And this is another cross section with the interaction diagram of the ACI, which this particular shape due to the strength reduction factor. For steel structures, we have another two new codes, which is for American codes, the bridge, and for the AESTO bridge design. We after performing the code checking, we will have these typical results depending on the type of checking. If we check members for tension, for compression, for bending. In this case, we check for compression for flexural buckling, and we have in this case these results. The same for the 14th edition of the AISC. We have these results. Okay, I can open the. If we go to CivilFEM, as I told you, that we have a new launcher. We can go here. CivilFEM. We have it here. We can choose here the working directory, and the job name, and we want to input a macro. We can do it. We just run CivilFEM for ANSYS, and we will have our environment. Okay, the environment is always the same. So in this case, I want to show you just a model. This is a truss model. This can be, of course, always done by using the typical procedure, defining our nodes and elements by direct element definition, or by creating lines and then mesh them. Okay, then we apply loads. We'll see here which are the loadings. The loads are just a force here, and it's just restrained at these ends. A vertical force, and we just solve as usual, going here and solve the analysis. It's already solved, and then we go after that. Before solving, of course, we always have to define our CivilFEM materials. In this case, it's a material from the Eurocode, number 3. And then we can define our cross section. We have a complete library of sections here, as you can see, and all the properties are defined. And always we define our beam properties. So we can assign different sections to different locations. After solving, we go to CivilFEM post-processor, and we will have our as well as we have the lot steps solved in ANSYS. We can click by load step, and then we can plot typical results. All these results, but as well in CivilFEM we can have our results as well by reading our lot step and having here our typical CivilFEM results, which are forces and moments. and we can perform here code checking. Depending on, in this case, we have the structural steel, and we have these complete checking types.
And the checking types are the different articles, the article formulations that are defined in the codes. We follow all the steps of the codes and standard with the formulation that are proposed by the codes.
In this case, we perform a bending check type, and all the results are described here. The results are the yielding limit state, the buckling limit state, the lateral torsional, and well, the required flexural strength, plastic bending moment. So we have them here, plot results, and we have them here. Example, all the typical results are here. And always we want to know which is the total criterion. If it's below 1, the section is okay. If it's above 1, the section must be redesigned.
The total criterion is the ratio between the demand and the capacity. It depends on the sort of checking we are doing. If that is for bending, so the design, the ratio between the design bending moment and the capacity of the section. Well, that ratio, if that is less than 1, section is okay because the demand is less than the capacity. And here you can see the results. It's 0.44, the maximum value. So this section is okay, and this can be like a sort of safety factor for that criterion, and that is the ratio that is proposed by the codes and standards.
Mm-hmm. Yeah. So other new enhancements for this new release of 17.1 is the cell cracking check. The cell cracking check can be done following the ACI 318 codes and the Eurocodes. To perform this, a new definition of bending reinforcement is created, has been developed, which is the spacing and diameter. So before we can only set a ratio of the total amount per length, and now we can set a spacing and a diameter.
So well, now it is possible to perform code checking for bending for cells, also out of plane shear and in plane shear for some codes, and now cracking checking. It's added to all these sort of checking types we have for cells, and we also have them all for beams. And also, as you know, these capabilities of checking and design for cells and beams in CivilFEM are extended to solid element models. If you create a model with solid elements, CivilFEM can perform cuts to those models, integrate stresses, and check and design by code, obtaining reinforcement amounts. So now we cover all the checking needs for cell, beams, and solids.
Yes, we will show you an example to show you this new shell crack checking for serviceability limit states. And we can start, we usually talk about the ANSYS mechanical APDL, but this time we can start, of course, with the other ANSYS environment, which is the workbench environment. If we can create our geometry here, our geometric model, using all the ANSYS tool geometry tools and capabilities, or we can import the file, the geometry file, using any other CAD software. So as you know, you can perform then our mesh and set some loadings. So in this case, we just set two different load steps. One is it's a simple load steps. The first one will have ultimate limit state coefficients, which is the wind and self-weight. And the second last step will just have the loads without any coefficients or coefficients set to unity, because we'll use them for the serviceability limit state. So the difference between the first and second last step is just only the coefficients for the different limit states checking.
Yes, so it's a simplified model that we are solving only one ultimate limit state combination and one serviceability limit state combination.
We used shell elements to define this hyperboloid roof shape, and we solved it. Once we solve it in Workbench, or we can create it's automatically created the input file. What we need to launch this analysis in CivilFEM into the ANSYS mechanical APDL environment. So if we have our file, where we go inside the ANSYS working folder, and we can open this ds.dat file, which is just a file like this, which will contain all the information about the node connectivity and elements and loads. So we just
this file is a log file, a command file with all the information of the model. So we can use that macro to import the model from Workbench environment to classic ANSYS environment. That CivilFEM works in the classic environment, which is much adequate for civil engineering.
Here we have it, our model. It's already here.
In this way, we have created the model in Workbench and imported into CivilFEM for ANSYS.
Yes, and now as our model is already solved, we don't need it, and we don't need to solve it again. We just need to follow a process to obtain the CivilFEM results. As you know, ANSYS has its own results file, which is the RST, and CivilFEM has another its own results file, which is the RCB. To create these files, we need to follow a process which is explained here in this log file. Or we can do it with the graphical user interface as well. The first is to select always the codes we are going to use. In this case, we want to use the ACI 3, the last implemented one, the 2014. Then we can define our materials, which are here. Well, we have to replace the ANSYS material.
ANSYS materials, example in this case for concrete, has less information than CivilFEM material properties. ANSYS only has concrete properties for solving, elasticity, mechanical property, elasticity modulus, and so on. But CivilFEM also needs some code properties for checking and design. So that is the reason we have to override ANSYS materials with CivilFEM materials, because they have extra information like safety factors, stress-strain diagram of concrete, parabolic, rectangular one for calculating the interaction diagram, and many other information that ANSYS material model
these are the properties which are defined here.
Design diagram, that is, this design diagram is used to check and design by code. You can modify those data, and also here you have the strain limits for the pivot diagram for calculating the interaction diagram. And
as you know, you know that some properties are time dependent. So in case we want to perform a nonlinear evolutive or construction analysis, we can use these different edges of concrete for for any property. So once we have defined our material for concrete and for reinforcing steel, you must define the next thing, which is the shell vertex, which is the same properties as coming from the thickness, material.
Well, in the same way, there are some missing properties in ANSYS materials that needs to be overwriting with CivilFEM ones for code checking. In the same way, for cross sections, shell vertex, ANSYS data is only material, concrete, and thickness. But we also need some extra data like mechanical cover, reinforcement amount.
Yes.
We would like to define.
Here we have them.
Some extra information that that we need to define. So that is the reason of just overwriting this cross section with CivilFEM ones to have this information.
Yeah, for the first lot step for the ultimate limit state, we just need to set the material and the mechanical cover. If we're going to perform just axial and bending plus bending code design, but as you can see here, we have different tabs to define other type of reinforcement for shells, for shear reinforcement and in plane shear reinforcement.
Here we also have the HCLPF properties. This is other checking type we have. We will explain later. It's different that checking by code. It's a different procedure.
Mm-hmm. Yes.
We will explain later.
Yes. We set here the thickness, for example. We use the ones set here in our the same thickness that is coming from the ANSYS workbench model, or we can everything that has been done using the graphical user interface can be done using the log file. Of course, always in CivilFEM we must define the beam or shell property to assign correctly the material shell vertex. In this case, we don't have a cross section, so we can do the same as copying and pasting the APDL script, and we have, so you can see here that we have it already defined, and the same for the beam and shell, the shell property. Then, okay, this is the process to define our results file, which is the RCB. First of all is to point to ANSYS results.
Well, if you remember, in the workbench model, we have solved two different load steps. One is for the ultimate limit state combination, and the second one is for the serviceability limit combination. So we are going to use the first one to calculate reinforcement amount. We are going to design the model for ultimate limit state using the code ACI 318 and calculate reinforcement amount. So with that reinforcement amount, we are going to place an equivalent reinforcement amount with spacing and diameter, and then check again the model for cracking checking with the second load step. The second load step, which is the serviceability limit state combination.
Yes. So the process is first to point to the ANSYS results,
the workbench result we calculate,
and then create the CivilFEM results. With this command, we create the RCB file results for the ultimate limit state.
So we are creating from the workbench result file, which name is roof and has two load steps. We are creating two different result files. One is going to be called roof ultimate limit state.
Go here,
and the second one is the serviceability.
You can see here we have two load steps. One for the for the ultimate limit state, and the second one for the serviceability limit state. So if you want, we can plot different results for each load step. This is the first one, and we can go to the second one, last step number 2. Okay. Then, as we told you, we have to create the CivilFEM results. After performing this, launching these commands, we'll see that we have here, we will have this. If we perform this, after pointing the first one, okay, then we will have our first load step in CivilFEM. For example, if we have here our model, if we want to perform a code checking, we can just select our shell elements, and we can read results. We can plot a result if you want to see results. For example, bending moment for this first load step of the ultimate limit state. We'll see our shell for shell elements bending moment. You'll see here, as we have a lot of elements, will take much or less time depending on your machine. Here we have. And if we want to perform, for example, I will reselect, for example, some elements. If you want to perform a code checking, for example, if you want to select these elements, the process will be just design by code, shells, and we want to perform a orthogonal regression method. We want to design our reinforcement. We will see the design reinforcement for these shell elements that are here selected. We can do, of course, we can do it with the full model, but here we just want to check this or design these elements to see the total reinforcement amount, and to set later accordingly the cracking properties. So here we can see all this in the international system. We see here the reinforcement amount and x the top face following the x direction. Then
here results you can see the value on the right with those colors. This is in the length unit you are using. In our case, it's meters.
Square meters. So square meter per length.
This is the value of this reinforcement is square meter per meter. So you can see that it could be about 4.7 square centimeters per meter, the reinforcement amount we need. That's if we are calculating this for the ultimate limit state, so we can convert this value, the needed reinforcement amount for ultimate limit state, we can convert it in spacing and diameter in the preprocessor, and performing a cracking checking for the serviceability limit state.
Yes, for the serviceability limit state, the process will be the same. It will be pointing to the ANSYS results. We copy and we create another file.
What we are doing is pointing to the result that was created in Workbench environment. and then we point to that result and just generate CivilFEM result file. And then with these results, we are going to use them for cracking checking.
So here we have it, but in this case we have just solved the serviceability limit state. In this case, as we have already the reinforcement amount coming from the code design, we can go and change, insert here, edit our cracking reinforcement properties, which will be spacing and the diameter of the bar.
Well, for cracking checking, it is needed. It's needed to be defined the spacing and diameter for the software to be able to calculate cracking checking for checking. So we need to set these values in the preprocessor.
Yes, as we already know, which was the maximum reinforcement amount from the other design, we can accordingly set the spacing and diameter of this.
Well, cracking checking is available for HCI 318 and also for the Eurocode too. So for cracking checking, we are going to use now the Eurocode for seeing both. You can perform also with the HCI code.
Yes. To perform a code checking or crack checking, we just go to the code design menu and check by shells by cracking. You will see this window. You just need to fill in all the properties according to this code.
For the Eurocode 2, the code and the article 7.3.4, we have the indications of how to calculate crack width from forces and moments. And with this code, what the CivilFEM does is compare the allowable crack width that has to be set by the user. We compare it with the one that is calculated by CivilFEM using the code specifications. And then we give a safety factor, a total criterion, that is the ratio between the allowable between the crack width and the allowable crack width. So if that safety factor is greater than 1 or less than 1, the section is okay or not okay. The crack width is greater or less than the allowable one. And that is for the Eurocode too. For the ACI 3118, the specification is different. The code calculates the needed spacing, and well, the code checking is based on the spacing, the needed spacing for the ACI code specification.
Yes, as already performed the crack checking, you will see all the available results for this structure. After setting in the cell vertex all the definition of, you see here, these are the results. If you don't want to set a scale, here we have the total criterion of the section, and we have other.
But this total criterion. This total criterion is, you can see, is less than 1, so it means crack width is less than the allowable one. We can plot which is the crack width, that is this value.
Yes. Always you need to set the spacing and diameter in the cell vertex in order to perform a crack checking. In this case, for shells, it will be the same for beams, but the new capability for this 17.1 version is the cracking for shells.
Well, here you can see the crack width, that it's in this case it's very small.
That's in meters.
This configuration of the shape of this roof is working mainly on compression, so we don't have much tension in the concrete, so crack width is very small. Also, we can plot other typical results. We can plot is here sigma x, that is the stress reinforcement, and these results can be plotted in x and y direction. The element axis, x and y, that we can reorientate them following the orientation we would like to give to reinforcement. So we first orientate the element axis, and then after solving, CivilFEM calculates reinforcement amounts in those directions, x and y, for the ultimate limit states. And for cracking checking, also CivilFEM calculates crack width in x and y direction. Mm-hmm. So you can see the results are here. You have double results for x and for y direction.
Yeah, another result is the position of the crack, and if the value is 1 or -1, if it's 1, the crack will be located in the top face, and if it's -1, the crack will be located on the bottom face. You can see, depending on our value, it goes from these values. You will see the position inside the section in y direction.
The crack in top or bottom,
depending if it's in top or bottom. Okay, so to summarize the process, coming in this case from a workbench model, after creating the geometry, the mesh, loading and solving, we for the different load steps, first load step including only the coefficients for ultimate limit state, and a second load step including only the unitary coefficients for the serviceability limit state. Then we read the input file, the DAT file, into the ANSYS mechanical APDL, and then we create both of the CivilFEM results file. One for the ultimate and the other one for the serviceability limit state. For the first one, we perform a reinforcement design after having the amount of the design for each direction. We can place in the cell vertex the properties or the definition of the spacing, the diameter of the bar, and the spacing. We can set these typical measures, the dimensions, or we can use the HDM ones, or set another dimensions if we want. After this, we point to the second results, to the serviceability limit state results, and we perform a crack checking. That will be the process to cover typical civil engineering analysis. So if we go back to our presentation, after this capability, we're going to show you another capability which was implemented in another version, but it wasn't explained conveniently.
Well, this new capability is what we call the seismic margin assessment, and that is other way to check and design our structures, also following the different codes and specifications. So, well, after designing or a previous constructed structure, and we would like to evaluate it. So, well, one of the structural engineers, one of the questions that they also used to have is that is if we have sufficient margin beyond to design combinations, and what could happen if we have some seismic loads over the design ones, if they will have a ductile behavior or a collapse, and also to identify the weak parts of the structure to improve the capacity. So, well, this is mainly focused for for nuclear power plants, but also it can be applied to any structure. And this is based, that is the reason that that it's focused on nuclear power plant. It's based in the EPRI code and also in Nuremberg specifications. And well, this is a method to quantify this capacity, the section capacity or the margin that is over the design loads, and that the structure can support higher load conditions. So this methodology is also described with the term high confidence of low probability of failure, that is described in these codes. And well, the idea is calculating using the seismic demand that we have. This seismic demand could be, depends on the codes. It could be a review level of earthquake or any other type of seismic of spectra, depends on the different parts of the world, that is higher to the design basic earthquake. And after setting this spectra in CivilFEM, CivilFEM calculates also seismic capacity of the cross sections using the active codes, taking into account this capacity, and also taking into account those inelastic energy absorption that can happen with high seismic loads for ductile sections, and those properties can be seen here in the cell vertex that we saw before. Here, these properties of this is, as you can see, the inelastic energy absorption for the different forces and moments. In this case, it's set to 1, but they can be with a value higher to 1. That is the ratio between the ductility ultimate capacity and the elastic value. So what CivilFEM does is instead of using the ultimate limit state combination and give a safety factor of that, what CivilFEM does is increase the seismic response of the structure, increase the seismic demand. These seismic results from the response spectra combination is this is increased until the capacity of until the section collapse, and then the results of this code checking is the seismic level in terms of peak ground acceleration that where failure is likely to occur. So an example here, we are plotting this roof of a nuclear power plant. In this part, we are plotting that value, and the results we are plotting here are in terms of peak ground acceleration that defines the spectrum level that creates the failure of these different beams of the roof. And we can analyze also the reason of the failure. That is an example for a spectrum of 0.17 Gs. Here, these beams are failure, and also we can analyze the failure if that's due to shear, bending, or whatever. And well, this tool can be used to calculate also the safety factor of different loads. Any sort of overload can be used with this tool to increase that overload until failure happens, and see the weak points of the structure and just reinforce them and improve the global capacity of the model. Also, other tool that we have for seismic analysis is the option. This is also other option that is used for seismic margin calculation, is calculate all the possible signs of the model for bending and axial forces. Instead of after performing the response spectrum analysis, all values are in absolute value. But CivilFEM analyzes the 4 possibilities: bending moment plus axial force positive, bending moment positive, axial force negative, both negatives, and bending moment negative and both positive, and analyze the worst situation. So analyzing the worst situation, taking into account the forces and moment signs, and increasing the seismic response until the model failure, CivilFEM is able to give in a conservative way the ultimate the values for the spectra that collapse the structure.
Okay. If you have we need more information, you can see here the contact emails and names. Thank you very much.
Well, thank you for your attention.
Bye.